the foundation of nightly repair, facts 1 to 10. As you settle into this moment, preparing your body and mind for rest, know that something truly remarkable is about to begin. Each night, as consciousness fades and the world around you grows quiet, your nervous system embarks on an extraordinary journey of restoration and renewal. This isn't simply rest in the passive sense. Rather, it's an active, intricate process of healing that unfolds in layers throughout the night, touching every neuron, every synapse, every delicate connection that makes up the vast network of your being. Let's begin with what happens during the deepest phases of your sleep, those moments when you drift furthest from waking awareness. During deep, slow-wave sleep, your body opens what we might call a maintenance window for your nervous system. In these precious hours, tissue growth and repair accelerate throughout your body, but nowhere is this more pronounced than in the intricate landscapes of your brain and nerves. Damaged nerve cells receive attention they've been waiting for all day. The supporting cells that cradle and nourish your neurons also begin their own repair work. It's as if a team of microscopic architects and builders arrives on site once you've closed your eyes, ready to restore what the day has worn down. This repair work is orchestrated by a remarkable substance called growth hormone, released in generous waves during these deep sleep phases. Growth hormone acts as a master signal, stimulating the regeneration of nerve cells and countless other tissues throughout your body. When sleep is restricted or fragmented, this vital hormone decreases, and the regeneration it triggers slows down significantly. But tonight, as you allow yourself to sink deeper into rest, growth hormone flows freely, touching every cell that needs renewal, encouraging them to rebuild, to strengthen, to prepare for another day. While this cellular repair unfolds, another extraordinary system awakens in your brain. Scientists call it the glymphatic system, and it functions as the brain's own specialized cleaning crew. During sleep, this system ushers cerebrospinal fluid through your brain tissue in rhythmic waves, clearing away the metabolic waste that accumulates during your waking hours. Among the debris it removes are proteins like beta-amyloid and tau, substances that, when allowed to build up, are linked to neurodegenerative diseases. During slow-wave sleep specifically, this clearance process becomes remarkably efficient, boosting waste removal by roughly 60 to 90% compared to when you're awake. Night truly becomes prime time for your brain's deep detoxification work. To make room for this cleansing process, your brain does something quite beautiful and surprising. As you sleep, particularly during the night hours, levels of norepinephrine, a chemical associated with alertness and stress, fall significantly. When this happens, your brain cells actually shrink slightly, and the spaces between them expand. This expansion might sound concerning, but it's actually profoundly beneficial. It lowers the resistance to fluid through neural tissue, allowing that cleansing cerebrospinal fluid to move more easily through every pathway and channel. The waste products that built up during the day can now be swept away more efficiently, and overall balance in the brain is restored. As this physical cleaning unfolds, your synapses, those crucial connection points between neurons, undergo their own form of reset and strengthening. Throughout the day, as you learn, experience, and interact with the world, countless new synapses form. Some of these connections are important and should be preserved. Others are less crucial, random noise in the system. Sleep provides the opportunity for your brain to decide which is which. Important connections formed during the day are selectively strengthened at night, while less useful ones are gently weakened or pruned away. This process, fundamental to neuroplasticity, prevents your neural networks from becoming overloaded. It helps your neurons fire more efficiently and protects your circuits from the continuous stress of maintaining every single connection that was ever made. This selective strengthening process is intimately connected to memory consolidation, another profound gift that sleep brings to your nervous system. During both REM and deep sleep, memories and skills you accumulated during the day are carefully transferred from temporary short-term storage networks to more permanent, long-term ones. This isn't a simple filing process. Instead, it involves reactivation and fine tuning of circuits in your hippocampus and cortex. The pathways that were stressed during the day as you learned and remembered are now given the chance to stabilize, to integrate new information smoothly into existing networks, and to repair any strain that learning imposed. Your memories become more stable, more accessible, and the neural pathways that hold them become healthier and more resilient. As all this restoration work proceeds, your body's stress systems, which may have been active throughout the day, finally have permission to power down. The sympathetic branch of your nervous system, the part responsible for your GHT or flight responses, grows quiet during sleep. Meanwhile, the parasympathetic branch, which governs rest and digestion, becomes more dominant. This shift creates a profound change in your internal environment. Cortisol and other stress signals decrease, giving your neurons a much-needed chance to recover from the constant state of arousal and emotional load they may have carried during waking hours. This isn't merely relaxation. It's a fundamental resetting of your stress response systems, allowing them to recalibrate and prepare to respond appropriately to tomorrow's challenges rather than remaining locked in today's tensions. This nighttime shift also brings relief to an inflammation within your nervous system. Adequate sleep helps regulate the immune signaling pathways that can, when overactive, release inflammatory molecules damaging to nerve tissue. During quality sleep, pro-inflammatory activity naturally reduces, giving damaged or irritated nerves the calm environment they need to heal. In contrast, when sleep is chronically lost, inflammation remains elevated, creating a harsh environment where neurological conditions worsen and nerve healing slows to a crawl. But tonight, as you rest fully, your immune system finds its proper balance, supporting healing rather than hindering it. All of these processes are guided and coordinated by the electrical rhythms of your sleeping brain. During slow-wave sleep, your brain produces large, synchronized waves that occur in rhythmic bursts approximately every 20 to 30 seconds. These aren't random fluctuations. They're coordinated oscillations that help drive the pulses of cerebrospinal fluid we spoke of earlier, supporting network-level resetting throughout your brain. These waves facilitate metabolic recovery in neural circuits, helping every region of your brain restore its energy reserves and prepare for the activity of a new day. Perhaps most encouraging of all is knowing that sleep protects your nervous system not just tonight, but over the long term as well. Consistent, quality sleep supports normal nerve signaling, maintains coordination between different brain regions, and preserves healthy cognitive function year after year. When sleep is chronically restricted, nerve cells gradually weaken. Pain pathways can become overactive and hypersensitive. Damaged nerves heal more slowly if at all. But there's hope even after periods of poor sleep. After sleep deprivation, the first nights of recovery sleep show boosted slow-wave activity as your brain prioritizes the deep, restorative processes it was denied. Even 2 nights of recovery can restore key connectivity in memory circuits like the hippocampus, though full cognitive recovery may require more time. This resilience, this capacity to heal even after being deprived, is one of the nervous system's most hopeful qualities. Each night of sleep is an opportunity for renewal, a chance to undo some of the day's wear and tear, a moment when healing takes precedence over all else. Segment 2. Myelin, New Neurons and Autonomic Balance, Facts 11 to 20. As we continue our journey through the night's healing processes, we now turn to some of the more subtle yet profoundly important ways your nervous system repairs and maintains itself while you rest. These processes happen quietly beneath the surface of consciousness, yet their effects ripple through your entire sense of well-being, your mental clarity, and your body's capacity to respond to the world. One of the most crucial yet often overlooked aspects of nighttime neural repair involves myelin, the insulating sheath that wraps around many of your nerve fibers. Think of myelin as the protective coating around an electrical wire, allowing signals to travel quickly and silently from one part of your nervous system to another. During sleep, particularly at night, genes involved in building and maintaining this myelin become more active in specialized cells called oligodendrocytes. These cells, dedicated to producing and preserving myelin, work most actively while you sleep, supporting signal speed along your nerves and protecting the delicate axons within from damage over time. Without adequate sleep, this maintenance work falters, and the quality of myelin throughout your nervous system gradually declines. The creation of new myelin-forming cells also depends heavily on sleep. Oligodendrocyte precursor cells, or OPCs, are specialized cells that can mature into new oligodendrocytes when and where they're needed. During sleep, these precursor cells approximately double their rate of proliferation compared to waking hours. Remarkably, their growth correlates especially strongly with time spent in REM sleep, that dream-led stage where your eyes move rapidly beneath closed lids and your brain shows activity patterns surprisingly similar to waking. This suggests that REM sleep specifically plays an important role in myelin-related healing, supporting the creation of new cells that will go on to maintain the insulation your nerves depend on. But it's not just about creating new myelin. Sleep also helps preserve the quality of existing myelin sheaths. When sleep is lost or disrupted, the delicate balance of cholesterol and other lipids within myelin becomes disturbed. This makes the myelin sheath less stable, and as a result, nerve conduction slows down. The signals traveling along your nerves become less crisp, less precise. In contrast, Adequate sleep helps maintain exactly the right lipid composition in myelin, supporting healthy, fast nerve signaling throughout your body. This is part of why, after a poor night's sleep, your thinking may feel sluggish, your reactions slower. The very insulation around your nerve fibers hasn't had the chance to maintain its optimal state between different brain regions and preserves healthy cognitive function year after year. When sleep is chronically restricted, nerve cells gradually weaken. Pain pathways can become overactive and hypersensitive. Damaged nerves heal more slowly, if at all. But there's hope even after periods of poor sleep. After sleep deprivation, the 5 nights of recovery sleep show boosted slow-wave activity as your brain prioritizes the deep, restorative processes it was denied. Even 2 nights of recovery can restore key connectivity in memory circuits like the hippocampus, though full cognitive recovery may require more time. This resilience, this capacity to heal even after being deprived, is one of the nervous system's most hopeful qualities. Each night of sleep is an opportunity for renewal, a chance to undo some of the day's wear and tear, a moment when healing takes precedence over all else. As we continue our journey through the night's healing processes, we now turn to some of the more subtle yet profoundly important ways your nervous system repairs and maintains itself while you rest. These processes happen quietly beneath the surface of consciousness, yet their effects ripple through your entire sense of well-being, your mental clarity, and your body's capacity to respond to the world. One of the most crucial yet often overlooked aspects of nighttime neural repair involves myelin, the insulating sheath that wraps around many of your nerve fibers. Think of myelin as the protective coating around an electrical wire, allowing signals to travel quickly and efficiently from one part of your nervous system to another. During sleep, particularly at night, genes involved in building and maintaining this myelin become more active in specialized cells called oligodendrocytes. These cells, dedicated to producing and preserving myelin, work most actively while you sleep, supporting signal speed along your nerves and protecting the delicate axons within from damage over time. Without adequate sleep, this maintenance work falters, and the quality of myelin throughout your nervous system gradually declines. The creation of new myelin-forming cells also depends heavily on sleep. Oligodendrocyte precursor cells, or OPCs, are specialized cells that can mature into new oligodendrocytes when and where they're needed. During sleep, these precursor cells approximately double their rate of proliferation compared to waking hours. Remarkably, their growth correlates especially strongly with time spent in REM sleep, that dream-led stage where your eyes move rapidly beneath closed lids and your brain shows activity patterns surprisingly similar to waking. This suggests that REM sleep specifically plays an important role in myelin-related healing, supporting the creation of new cells that will go on to maintain the insulation your nerves depend on. But it's not just about creating new myelin. Sleep also helps preserve the quality of existing myelin sheaths. When sleep is lost or disrupted, the delicate balance of cholesterol and other lipids within myelin becomes disturbed. This makes the myelin sheath less stable, and as a result, nerve conduction slows down. The signals traveling along your nerves become less crisp, less precise. In contrast, adequate sleep helps maintain exactly the right lipid composition in myelin, supporting healthy, fast nerve signaling throughout your body. This is part of why, after a poor night's sleep, your thinking may feel sluggish, your reactions slower. The very insulation around your nerve fibers hasn't had the chance to maintain its optimal state. Beyond myelin, sleep appears to favor the birth of entirely new neurons in certain regions of your brain, particularly in the hippocampus, a structure crucial for forming new memories. This process, called adult neurogenesis, was once thought impossible, but we now know that new neurons continue to be born throughout life in specific brain regions. Sleep deprivation clearly inhibits this production of new neurons, effectively closing down one of the brain's pathways for renewal. But when normal sleep returns after a period of chronic loss, something beautiful can happen. There can be a rebound and overshoot in new neuron formation as your circuits begin to recover. Your brain, given the chance to rest again, responds by ramping up its production of fresh neurons, actively working to restore what was lost. This recovery of new neuron production is closely tied to the recalibration of stress hormones in your body. Prolonged sleep deprivation elevates glucocorticoids, stress hormones like cortisol, to levels that suppress neural cell proliferation throughout the brain. When these hormones remain high, neural stem cells and the supporting cells around them struggle to do their work. But normal nights of sleep help bring these hormone levels back toward a healthy baseline, easing the pressure on these crucial cells. With stress hormones returning to appropriate levels, neural stem cells can resume their essential functions, and the brain's capacity for self-renewal gradually returns. As these cellular processes unfold, your autonomic nervous system, which controls so many automatic functions of your body, undergoes its own careful retuning. Across a normal night of sleep, parasympathetic activity, associated with rest, digestion, and recovery, strengthens steadily. At the same time, sympathetic activity, linked to alertness and stress responses, falls away. This autonomic reset protects blood vessels and organs that your brain depends on for proper function, reducing wear on the neural circuits that regulate everything from your heartbeat to your breathing. Over many nights, this repeated shift helps establish a healthier baseline for your autonomic function, making your body more resilient to stress and better able to maintain internal balance. The circuits that control sleep and waking themselves also receive maintenance during the night. Sleep promoting neurons in a region called the ventrolateral preoptic nucleus become active as you drift off, and they actively inhibit wake-promoting cells elsewhere in your brain. This inhibitory activity does more than simply allow sleep to occur. It also protects arousal networks from constant firing and the metabolic strain that would result from never having a break. Your wake-promoting systems, which work so hard during the day to keep you alert and responsive, need this nighttime rest just as much as you do. Interestingly, the timing of physical exercise during the day can influence how effectively these autonomic systems reset at night. Morning exercise tends to enhance parasympathetic activity during the following night's sleep, creating conditions particularly friendly to recovery and restoration. Evening exercise, while still beneficial in many ways, can keep sympathetic activity somewhat elevated even into sleep, slightly reducing the depth of the autonomic rest you achieve. This doesn't mean evening exercise is harmful, but it does illustrate how the timing of our daily activities can influence the quality of nighttime nervous system repair. The proliferation of new cells in regions like the hippocampus doesn't happen randomly throughout the day and night. Instead, it follows daily rhythms that track your sleep-wake patterns. Cell division tends to cluster at specific times, coordinated with your circadian clock. Aligning your sleep with natural circadian timing helps coordinate when neural stem cells divide versus when they integrate into existing circuits. This temporal organization ensures that new cells are born at the right time and in the right metabolic context to have the best chance of surviving, maturing, and contributing to brain function. All of these nighttime processes work together to protect something crucial: your long-term nerve conduction speed. When sleep is repeatedly cut short, changes accumulate in myelin and oligodendrocyte health, leading to measurable delays in how fast nerve signals travel. Over time, this slowing can affect everything from your reaction time to how quickly you can think through complex problems. But regular, sufficient sleep helps preserve the fast, synchronized communication across brain networks that you need for clear thinking and stable mood. The protection sleep offers isn't just for tonight or tomorrow. It's an investment in maintaining the speed and efficiency of your nervous system for years to come, allowing you to age with your mental faculties better preserved, your responses quicker, your thoughts clearer. As night deepens and your sleep continues its restorative work, we now explore the role of some remarkable cells and chemicals that maintain the health of your nervous system in ways you might never have imagined. These are the night gardeners and balancing forces that work tirelessly while you rest, pruning, cleaning, and rebalancing the intricate networks of your mind. While you sleep, specialized immune cells in your brain called microglia become extraordinarily active in a particular way. During the day, when norepinephrine levels are high and your attention is focused on the external world, microglia remain relatively quiet. But as you sleep and norepinephrine levels fall, these cells extend their delicate processes like branches, reaching out to make contact with synapses throughout the brain. They act as night gardeners, carefully pruning weak or unnecessary synaptic connections and helping repair tiny lesions in neural circuits that may have formed during the day's activities. This careful pruning isn't destructive. Instead, it's a form of careful maintenance, removing the excess so that what remains can function more efficiently and effectively. Working alongside microglia are astrocytes, star-shaped cells that have their own crucial role in maintaining brain health and supporting sleep itself. Astrocytes release a molecule called ATP that breaks down into adenosine, a chemical that builds what scientists call sleep pressure throughout the day. As adenosine accumulates, you feel increasingly sleepy, and once you finally do sleep, adenosine helps modulate how excitable your neurons are. During sleep, astrocytes also help adjust synaptic strengths and maintain overall balance in brain activity, preventing circuits from becoming overexcited and burning out. They're constantly monitoring and adjusting, making sure that no single group of neurons becomes too active or too quiet, maintaining the delicate equilibrium that healthy brain function requires. As this cellular work proceeds, the balance of neurotransmitters throughout your brain undergoes significant shifts. During wakefulness, your brain relies heavily on activating neurotransmitters like norepinephrine, serotonin, and histamine to keep you alert, responsive, and engaged with the world. But in REM sleep, these transmitters decrease dramatically or switch off entirely. This overnight cycling of neurotransmitters helps reset receptor sensitivity throughout your brain, ensuring that these chemical messaging systems will work properly. When you wake, without this nightly reset, receptors can become desensitized, requiring more and more neurotransmitter to produce the same effect, a process that underlies many forms of adaptation and potentially dysfunction. Two neurotransmitters particularly important for mood and motivation, serotonin and dopamine, receive special support from the deep phases of sleep. These stages help restore optimal levels and tone in both serotonin and dopamine systems, which in turn stabilizes mood and motivation when you wake the next day. When sleep is disrupted, these systems can remain imbalanced, leaving you more vulnerable to anxiety, low mood, and problems with reward processing and motivation. The malaise and emotional fragility that often follow a sleepless night aren't just in your imagination. They're FLECT real changes in the neurochemical balance of your brain, changes that proper sleep would have prevented. Sleep also carefully modulates the immune signaling molecules called cytokines, substances like interleukin-1 and TNF-alpha that in influence both sleep itself and inflammatory responses throughout the brain. At night, this tuning process helps keep immune activity in a healthy, moderate range, limiting chronic neuroinflammation that can, over time, injure neurons and contribute to neurodegenerative diseases. The immune system and nervous system are in constant communication, and sleep provides the calm environment where that communication can be clear and productive rather than chaotic and potentially harmful. This immune-brain communication follows circadian and sleep-dependent rhythms, coordinated through neuroendocrine and sympathetic pathways. The nervous system tells the immune system when it's time to be vigilant and when it's time to focus on repair. The immune system, in turn, provides information to the brain about the state of the body. Proper sleep allows immune cells to time their surveillance and repair activities in the brain far more efficiently than they could during waking hours, when other demands compete for resources and attention. One of sleep's most important functions is preventing what researchers call synaptic saturation. During waking hours, as you learn and experience new things, synapses throughout your brain gain strength. This is how learning happens at the cellular level. But if this strengthening continued unchecked, synapses would eventually reach a point where they couldn't get any stronger, making further learning impossible. Non-REM sleep promotes a subtle global downscaling of synaptic weights throughout the brain, reducing the overall strength of connections while preserving their relative differences. This means that important, strong connections remain stronger than less important ones, but the whole system shifts down, making room for new learning the next day. Your networks remain flexible, capable of adapting and growing rather than becoming rigid and saturated. This downscaling process is supported by dynamic structural changes in astrocytes themselves. During sleep, astrocytic processes that normally wrap around synapses retract somewhat, altering how the neurotransmitter glutamate is cleared from the spaces between neurons. This change promotes the synchronized slow waves that characterize deep sleep, those rhythmic oscillations that help drive so many of the restorative brain processes we've been exploring. The physical structure of your brain literally changes shape slightly during sleep, optimizing itself for different kinds of work than it performs during waking hours. All of these processes are enforced and protected by sleep homeostasis, a powerful regulatory system that ensures you get the sleep you need. As you stay awake, adenosine builds up continuously, increasing sleep pressure with each passing hour. This adenosine signaling, largely dependent on astrocytes, helps enforce recovery sleep when you've been awake too long. It's a homeostatic mechanism that prevents chronic overuse of attention and memory circuits, reducing long-term wear and tear on the systems you depend on for thinking, learning, and remembering. Without this mechanism, you might push yourself far past healthy limits, accumulating damage that could never be fully repaired. Finally, research has revealed that even short-term sleep loss can rapidly rewire certain circuits, particularly those involved in reward processing. A single night of lost sleep increases dopamine release and triggers synaptic remodeling in prefrontal reward-related circuits. This can temporarily alter how you perceive rewards and make decisions, often making immediate rewards seem more appealing while long-term consequences seem less important. But remarkably, subsequent normal nights of sleep help these circuits stabilize again, demonstrating how quickly the nervous system can adapt and recover when given the opportunity. Your brain possesses a resilience that, while remarkable, still depends on your willingness to provide the sleep it needs to reset and repair. We now move into deeper territory, exploring how the fundamental rhythms of day and night themselves orchestrate the healing and maintenance of your nervous system. The processes we'll explore in this segment reveal that nighttime repair isn't just about sleep, but about being aligned with the ancient, cosmic rhythms that life evolved to follow over billions of years. Deep within your brain, in a small region called the suprachiasmatic nucleus, sits what scientists call your master circadian clock. This tiny cluster of neurons acts as a conductor for the vast orchestra of cellular processes occurring throughout your body, coordinating them all with the 24-hour cycle of light and dark that our planet turns through. One of the most fundamental processes it coordinates is DNA repair in brain cells themselves. Research has revealed that nucleotide excision repair, a key pathway for fighting damage to DNA, is much more active in brain cells during the biological day than at night, showing that even genomic repair is under circadian control. This daily rhythm in DNA repair is tied to oscillations in a repair gene called XPA, which the core clock proteins clock and BMAL1 help regulate. These clock proteins rise and fall in abundance throughout the day-night cycle, and they directly influence when genes involved in DNA repair are turned on and off. The timing matters because DNA repair is energy-intensive work, and the circadian clock helps ensure this work happens when conditions are most favorable, when the cell has adequate resources and faces fewer competing demands. The suprachiasmatic nucleus doesn't keep time in isolation. Instead, it coordinates day-night timing signals to brain regions all across your brain and beyond. By controlling hormones, body temperature, and autonomic tone across the full 24-hour cycle, it indirectly times when neural tissues should focus on active processing versus maintenance and repair. This means that even if you somehow forced yourself to stay awake all night, many of your cells would still be trying to perform nighttime maintenance functions because they're responding not just to whether you're asleep, but to deeper circadian signals that track the turning of the earth. Within the neurons of the suprachiasmatic nucleus themselves, something remarkable occurs. These cells show circadian changes in ion channel expression and activity, which alter how easily they can be electrically excited over the course of the day-night cycle. During the day they fire more readily. At night their activity decreases. These rhythmic shifts in electrical properties help generate stable daily patterns of neural firing that keep the rest of your nervous system on a predictable schedule. It's a beautiful example of how electrical, genetic, and molecular processes all interact to create the rhythms of life. These clock genes aren't just timing DNA repair and electrical activity. They also participate in maintaining adult neural stem cells, those precious cells in your brain that retain the capacity to give rise to new neurons throughout your life. Circadian clock machinery helps regulate when these stem cells should divide and when they should remain quiet, waiting. Disrupting these clock signals can impair stem cell maintenance and may reduce your brain's long-term capacity for self-repair, showing just how deeply the rhythms of night and day are woven into your brain's ability to renew itself. As darkness falls each evening, your pineal gland, a small structure deep in your brain, begins releasing melatonin into your bloodstream. This hormone of darkness travels throughout your body, binding to specialized receptors widely distributed in your central nervous system, including the hippocampus and thalamus. This melatonin signaling helps align neuroplasticity and cellular repair processes with the dark period of night, when external demands on your nervous system are naturally lower. Melatonin isn't just making you sleepy. It's communicating time-of-day information to countless cellular processes, helping coordinate when repair work should intensify. The circadian genes clock and BMAL1 in your suprachiasmatic nucleus also influence when your brain is most efficient at learning and forming new memories. Their activity persists into the early evening hours, supporting periods where new learning and synaptic modification are still favored before deeper, more restorative sleep begins to dominate. This is why many people find the evening hours good for studying or creative work. The circadian system is still supporting active cognitive processing, though it's beginning its gradual transition toward the restoration that will dominate the deeper night. When circadian rhythms are disrupted, whether through mutations in clock genes, shift work, or simply irregular sleep schedules, the consequences for the nervous system can be significant. Disturbances in clock and related genes are associated with reduced total sleep time and sustained neural excitability, meaning that neurons don't get their normal daily downshifting period. When this clock-driven calming window is lost, neurons face more continuous activity and oxidative stress, which over time can erode long-term brain health. The wear and tear accumulates, and the nervous system ages more rapidly than it would with intact circadian rhythms. Even the neurotransmitter GABA, the brain's primary inhibitory signal, shows circadian rhythmicity in the clock center itself. GABAergic signaling in suprachiasmatic nucleus neurons oscillates across the day-night cycle, partly driven by clock and BMAL1 dependent transcription of GABA receptor subunits. Remarkably, changing GABA tone can also feed back to shift clock gene expression, creating a two-way conversation between chemical signaling and genetic timing mechanisms. This feedback helps the clock adjust and fine-tune itself, maintaining accuracy even as conditions change. The circadian clock also works in intimate partnership with cellular metabolism. Neural stem cells and other brain cells use metabolic cues, such as the cell's redox state and levels of the coenzyme NAD+, to interact with circadian clock machinery. This coupling allows energy-intensive repair and regeneration steps to occur at clock-specified times when resources are most available and competing demands are lowest. It's a beautiful EF-Phi science, ensuring that your limited cellular resources are used at the times when they can do the most good. Perhaps most importantly, maintaining a healthy circadian rhythm is itself neuroprotective. Studies have shown that aligned day-night cycles support cellular repair, metabolic EF-Phi science, immune balance and cognitive maintenance throughout the brain. In contrast, chronic circadian disruption, whether from night shift work, irregular schedules, jet lag or excessive light at night, weakens these protective patterns and increases risk for neurodegenerative diseases, mood disorders and cognitive decline. The simple act of going to bed and waking at consistent times, aligned with natural light-dark cycles, is one of the most powerful things you can do to protect your nervous system over a lifetime. Your brain evolved to expect these rhythms, to depend on them, and when you provide them consistently, you're giving your nervous system one of its most fundamental requirements for long-term health. As we continue through the night's mysteries, we now turn our attention to something that might surprise you. Your peripheral nerves, those nerve fibers extending throughout your body beyond your brain and spinal cord, have their own internal clocks that determine when they can best heal themselves. The insights we're about to explore reveal that the nervous system's relationship with time goes far deeper than simple daily rhythms of sleep and waking. Scientists have discovered that sensory neurons in the dorsal root ganglia, clusters of nerve cell bodies located along your spine that relay sensation from your body to your brain, contain an intrinsic 24-hour clock within each cell. This internal timekeeper profoundly affects how strongly these neurons can regrow their axons after injury. Their regenerative programs turn on more powerfully at certain night phase times, meaning that the capacity for nerve repair itself literally rises and falls across the course of each day. If a nerve is damaged, when that damage occurs may influence how well and how quickly it can heal. At the heart of this daily variation in repair capacity is the core clock protein BMAL1, operating right within these sensory neurons. BMAL1 directly regulates whole sets of what researchers call regeneration-associated genes, genes specifically involved in axon growth, guidance, and reconnection with targets. When BMAL1 is experimentally removed from these neurons in laboratory studies, their ability to activate this repair program and successfully reconnect with their targets after injury is greatly reduced. The clock isn't just marking time. It's actively controlling whether neurons can mount an effective healing response. This has led researchers to identify what they call peak hours for nerve regeneration. In mouse models of sciatic nerve injury, when the timing of damage occurs at certain late-night circadian phases, axon regeneration and target reinnervation are significantly higher compared to injuries that occur at other times of day. This shows that the night phase is not uniform in its healing properties. Some hours within the night are biologically more favorable for initiating neural repair than others, presumably when all the cellular machinery, resources, and signals align most favorably. The mechanism behind these peak hours involves epigenetic changes, modifications to how DNA is packaged that influence which genes can be easily turned on or off. During the circadian windows that favor regeneration, neurons show higher levels of an epigenetic mark called H3K27AC, associated with activating growth and repair genes. This time-of-day-dependent chromatin change essentially opens up the DNA, making repair programs more accessible and able to run more EF-Phi silently during periods when overall activity demands are naturally low. Your cells are using the clock to know when they can safely dedicate resources to repair without compromising other essential functions. Intriguingly, research has found that certain substances can amplify this clock-driven repair process. In animal studies, lithium, a medication often used to treat bipolar disorder, enhances axon regeneration after peripheral nerve injury, but only when the neuronal clock is intact and functioning. Lithium works by increasing BMAL1 expression, effectively amplifying the clock's nighttime regenerative signal and promoting stronger regrowth. This suggests that understanding and working with the circadian timing of nerve repair might lead to better therapeutic strategies for people recovering from nerve injuries. The benefits of aligning repair with the right circadian phase extend beyond simply growing new axons. When injuries occur in the optimal circadian window, regrowing sensory axons don't just elongate faster. They also reconnect better with their proper targets in skin and muscle weeks later. This suggests that the night-tuned repair program encompasses not just growth speed but also the accuracy of neural rewiring. The clock is helping to ensure that nerves don't just regrow, but regrow correctly, re-establishing the proper connections that allow sensation and movement to return with greater fidelity. This circadian timing of repair may also serve a protective function by limiting collateral damage during the healing process. By clustering intense regenerative gene activity into specific low-activity hours, the clock helps separate heavy repair work from peak periods of signaling and normal metabolism. This temporal separation may reduce conflicts over limited energy resources and lower the risk of oxidative stress during neural healing. Your cells can focus on repair when they're not also trying to maintain normal function, reducing the chances that something goes wrong in either process. The pattern of clock-dependent repair appears to be conserved across different tissues, not unique to nerves. Similar patterns have been observed in organs like lung and muscle, where disrupting circadian clocks also weakens regeneration. This supports the idea that the nervous system is using a shared circadian logic with the rest of the body, a universal strategy of scheduling repair into night rest periods when the organism as a whole is less metabolically active and less exposed to external challenges and damage. When core clock genes like BMAL1 are disabled in neurons through genetic manipulation in research animals, something telling happens. The usual night phase peak in axon regeneration simply disappears. Instead of seeing strong regeneration at night and weaker regeneration during the day, researchers observe weaker, more uniform regeneration at all times. This demonstrates that a healthy, functioning clock is absolutely required to get the full benefit of nighttime healing. Without proper circadian timing, the nervous system loses one of its most powerful tools for self-repair. Understanding these rhythms has practical implications that we're only beginning to explore. Because nerve regeneration has these circadian highs and lows, future medical treatments and rehabilitation programs might someday be scheduled to coincide with peak night phase repair windows. Aligning therapies, medications, electrical stimulation, or physical rehabilitation with these natural rhythms could potentially make each night's healing work more effective, speeding recovery and improving outcomes for people dealing with nerve injuries. The clock that turns within each of your cells might hold the key to optimizing how we help the nervous system heal from trauma, guiding us to work with the body's innate wisdom about timing rather than against it. Segment 6. Motor Control, Pain and Autonomic Refinement, Facts 51-60. As our journey through the night's healing continues, we now explore how sleep doesn't just repair individual cells, but refines entire systems of neural function. The processes we'll discover in this segment reveal how your brain uses the night to polish your movements, recalibrate your pain responses, and fine-tune the automatic systems that keep you alive without conscious thought. During sleep, something fascinating happens in the motor circuits that control your movements. Spinal and cortical motor networks replay recent movement patterns you performed during the day, a process that helps refine any motor commands and reduce what engineers would call noise in the system. This replay isn't random or purposeless. Instead, it strengthens the efficient pathways you used for successful movements and prunes away the clumsy ones, the unnecessary activations that made your movements less smooth or accurate. Over time, this means each motor neuron fires residential more precisely, with less wasted effort, reducing strain and the micro-injuries that can accumulate in motor neurons when movements are consistently inefficient or awkward. Sleep also brings profound relief to your pain processing systems. Throughout the day, especially if you're dealing with ongoing pain or stress, your pain pathways can become increasingly sensitive through a process called central sensitization. Your nervous system starts interpreting normal sensations as painful, amplifying signals that shouldn't hurt. Nighttime sleep helps reset sensitivity in these pain pathways, reducing this built-up sensitization and bringing your pain perception back toward normal levels. When sleep is disrupted chronically, these pathways never get this reset. They stay more reactive, which is why research shows such a strong link between chronic poor sleep and heightened pain perception. The pain isn't imaginary, but the volume knob on your pain system has been turned up, and only quality sleep can turn it back down. As night begins to settle around you, your nervous system receives a quiet signal. The signal is simple and ancient. It tells your body that the day's demands are over and that it is safe to rest. Without effort, without instruction, your nervous system begins to change its rhythm. The fast, alert signals that carried you through the day begin to soften. The background hum of readiness slowly fades. Your body does not shut down, instead it shifts into a different mode, a mode designed for repair, balance, and renewal. This transition happens every night, even when you are unaware of it, even when the day has been demanding. As your breathing becomes slower and more regular, the balance inside your nervous system gently shifts. The system responsible for urgency and action begins to quiet. The system responsible for restoration becomes more active. Heart rate slows. Muscles release subtle tension. Electrical signals traveling through nerves lose their urgency. Your nervous system begins to recognize stability. Darkness, stillness, fewer signals to interpret. These cues tell the brain it no longer needs to stay alert. Stress hormones begin to fall. Cortisol levels soften. Adrenal signals fade into the background. Neurons are no longer being pushed to respond quickly. They are allowed to settle into quieter patterns of activity. This quiet is not empty. It is purposeful. The nervous system has practiced this rhythm for as long as humans have slept. As the body settles further, attention turns inward. External information fades. Internal balance takes priority. Nothing needs to be solved. Nothing needs to be remembered. Your nervous system knows how to let go. And as this letting go continues, deeper processes begin to prepare quietly beneath awareness. As night begins to settle around you, your nervous system receives a quiet signal. The signal is simple and ancient. It tells your body that the day's demands are over and that it is safe to rest. Without effort, without instruction, your nervous system begins to change its rhythm. The fast, alert signals that carried you through the day begin to soften. The background hum of readiness slowly fades. Your body does not shut down, instead it shifts into a different mode, a mode designed for repair, balance, and renewal. This transition happens every night, even when you are unaware of it, even when the day has been demanding. As your breathing becomes slower and more regular, the balance inside your nervous system gently shifts. The system responsible for urgency and action begins to quiet. The system responsible for restoration becomes more active. Heart rate slows. Muscles release subtle tension. Electrical signals traveling through nerves lose their urgency. Your nervous system begins to recognize stability. Darkness, stillness, fewer signals to interpret. These cues tell the brain it no longer needs to stay alert. Stress hormones begin to fall. Cortisol levels soften. Adrenal signals fade into the background. Neurons are no longer being pushed to respond quickly. They are allowed to settle into quieter patterns of activity. This quiet is not empty. It is purposeful. The nervous system has practiced this rhythm for as long as humans have slept. As the body settles further, attention turns inward. External information fades. Internal balance takes priority. Nothing needs to be solved. Nothing needs to be remembered. Your nervous system knows how to let go. And as this letting go continues, deeper processes begin to prepare quietly beneath awareness. As the night progresses, cycles of sleep continue to unfold. Some phases focus more on physical repair. Others gently tend to memory and emotion. During these cycles, memory networks quietly replay fragments of the day, not as thoughts, but as patterns of activity. This replay helps stabilize learning. It allows experiences to be stored without emotional intensity. Stressful moments are revisited in a calmer chemical environment. The volume is turned down. Reactivity is softened. This is one reason sleep supports emotional balance. Neurotransmitters that influence mood and motivation are gently rebalanced. Reward circuits stabilize. Emotional signals become less sharp. Pain pathways are recalibrated. Sensitivity adjusts toward a healthier baseline. Throughout the night, immune signaling in the nervous system is carefully regulated. Repair is prioritized over defense. Inflammation remains contained. Motor circuits replay movement patterns quietly, refining efficiency and reducing noise. Nothing is rushed. Nothing is forced. The nervous system is simply optimizing itself, one gentle adjustment at a time. Even dreams, when they appear, are part of this process. They allow emotional material to move through the system without waking intensity. All of this happens while consciousness rests. And as these cycles repeat, stability deepens. As the night continues, repair processes gradually begin to taper. Circadian timing systems coordinate this transition gently. Nothing stops suddenly. DNA maintenance mechanisms complete their work. Damaged components are recycled. Protective systems reset. Peripheral nerves adjust sensitivity. Communication pathways remain clear. Blood pressure regulation improves. Breathing patterns remain steady and efficient. These adjustments protect both brain and body. As dawn approaches, the nervous system prepares without urgency. Chemical balances shift gradually. Neural circuits are refreshed. Protective systems remain in place. Even imperfect sleep contributes to this renewal. Even partial rest provides benefit. Night after night, these small acts of maintenance accumulate. They support resilience. They preserve clarity. They protect long-term function. There is nothing you need to do. Your nervous system knows how to restore itself. As awareness drifts further, this quiet work continues. Balancing, repairing, preparing, at its own pace, in its own time. And as rest continues, the nervous system remains awake in its own way, doing exactly what it was designed to do. As the night surrounds you, the nervous system begins a familiar transition, one that does not require thought, effort, or intention. It begins with small shifts, so small they are rarely noticed. Signals that once moved quickly now slow their pace. Urgency fades. The body senses that nothing is being asked of it anymore. The nervous system has learned over countless nights how to recognize this moment. The moment when the environment grows quieter, darker, steadier. Breathing naturally lengthens. The space between each breath widens just a little. Heart rhythm follows. This slowing is not a loss of control. It is a return to balance. The part of the nervous system responsible for constant readiness gradually steps back. In its place, systems devoted to repair and restoration step forward. Muscles soften in places you did not realize were holding tension. The jaw loosens. The shoulders settle. Electrical activity in the nerves becomes less sharp, less demanding. Signals still travel, but they do so gently now. The brain no longer scans the environment for change. It no longer prepares for response. Instead, it begins to listen inward. Stress chemistry begins to quiet. Hormones associated with alertness lose their influence. The nervous system recognizes that it has entered a protected window of time. A window where effort is unnecessary. Nothing needs to be solved. Nothing needs to be remembered. This is not sleep yet. It is the doorway. And as this doorway opens, deeper processes prepare to unfold. As sleep gently deepens, attention continues to withdraw from the outer world. Sensory information becomes less important. Sounds soften. Thoughts drift without direction. Inside the brain, activity begins to reorganize itself. Neurons that were busy coordinating complex tasks during the day are now freed from those demands. They no longer need to react quickly. This change allows the brain's internal environment to shift. Support cells move into a more active role. They regulate fluids. They manage chemical balance. Tiny spaces between brain cells widen slightly. This creates room for fluid to circulate more freely. This circulation is slow, steady, rhythmic. It gently carries away byproducts of daily activity, not as a dramatic cleanse, but as quiet maintenance. The slower the brain's electrical patterns become, the easier this process flows. Deepening sleep provides ideal conditions for this work. The nervous system is not passive here. It is highly organized, just not loud. Connections formed during the day are evaluated. Some are reinforced. Others are allowed to weaken. This fine-tuning prevents overload. It protects clarity. The brain is not erasing experience. It is preserving what matters and releasing what does not. All of this happens beyond awareness. The nervous system works best when it is not being watched. As the night moves on, deeper stages of sleep arrive. Brain activity slows further. Large networks of neurons begin to synchronize. These slow rhythms are deeply restorative. During this time, the body increases the release of substances that support tissue repair. This includes repair within the nervous system itself. Nerve cells benefit from this environment. So do the cells that support them. Insulation around nerve fibers is maintained and restored. This insulation allows signals to travel smoothly without interference. When insulation remains healthy, communication stays efficient. When it weakens, signals become noisy. Nighttime sleep helps prevent this. Inflammatory activity in neural tissue is kept low. Repair is prioritized over defense. Immune signaling becomes more precise, less reactive, more targeted. This protects delicate structures. Deep sleep also supports long-term signal reliability. It preserves coordination between distant brain regions. Nothing about this process is rushed. The nervous system understands time. It works slowly because slow work lasts. As sleep cycles continue, the brain enters phases devoted to internal integration. Memory networks quietly revisit fragments of experience, not as stories, but as patterns. This replay stabilizes learning. It helps skills and knowledge settle into long-term storage. Emotional experiences are included in this process. Moments that carried intensity during the day are revisited in a calmer chemical environment. The nervous system can observe without reacting. This reduces emotional charge. It does not erase experience. It softens its impact. Neurotransmitters that influence mood are gently rebalanced. Systems involved in motivation and reward stabilize. Pain sensitivity adjusts. Thresholds return toward healthier levels. Motor circuits replay movements, refining efficiency and reducing strain. Even dreams, when they appear, are part of this integration. They allow emotion to move without waking stress. The nervous system uses the night to untangle what the day compressed. Beneath sleep itself, another system continues its quiet guidance. The circadian clock. Every cell in the nervous system carries a sense of time. This timing helps coordinate repair. Certain processes are scheduled specifically for night hours. When energy demand is lower, when interference is minimal, DNA maintenance mechanisms become more active. Proteins that need replacement are identified. Damaged components are recycled efficiently. Neural stem cells are preserved. Future repair capacity is protected. This timing is precise, but gentle. The nervous system does not repair everything at once. It follows rhythm. This rhythm prevents conflict between signaling and repair. Night provides the space for both. The nervous system extends far beyond the brain. Peripheral nerves also respond to night rhythms. Sensitivity adjusts. Pain pathways recalibrate. This is why consistent sleep supports comfort and resilience. Communication between brain and body becomes smoother, less reactive. Blood pressure regulation improves. Breathing patterns stabilize. The autonomic nervous system practices calm regulation repeatedly. This practice carries into waking life. Night trains the nervous system to respond with less force and more precision. Night after night, small acts of repair accumulate. No single night carries all the weight. Resilience is built gradually. Sleep protects long-term nerve signaling. It preserves cognitive clarity. It supports emotional balance. Even imperfect rest contributes something. The nervous system does not demand perfection. It responds to consistency. Each night of rest reinforces the pattern that night equals safety. This learning itself is a form of healing.